So now we introduce the complex numbers, and a complex number is a combination of a real number and an imaginary number. So for example, 7 plus 5i is a complex number, and we call this part the real part, and the 5i in this case is called the imaginary part. So now it's possible to, if this was a 0i, it would be possible to think of this as the number 7 as a complex number. If 7 was a 0, it would be possible to think of 5i as a complex number. But 7 itself is a real number, and 5i is an imaginary number. And so when you combine them together, you consider the system of numbers, which is a combination of both reals and imaginary parts, then you get the complex number system. And so now the complex number system is a two-dimensional number system. Where would 7 plus 5i be? Well, we label this the real axis, what in algebra we usually call the x-axis, now becomes the real numbered axis. And so 1, 2, 3, 4, 5, 6, 7 real numbers take place along the horizontal scale, and imaginary numbers go up and down the vertical scale. So here's I, 2i, and 5i would be up here. There we go. So 7 plus 5i means going over 7 on the real axis and up 5i on the imaginary axis, and that would be approximately there. So here's the number 7 plus 5i, and I didn't label this. This is the imaginary axis. So it takes 2 dimensions to describe the complex numbers, and they're two-dimensional numbers. Now it turns out that the complex numbers are all you need to solve any kind of polynomial equation. And so as long as the coefficients of your polynomials were complex numbers, then you don't need anything larger than that. You don't need, say, a three-dimensional number system. So things are fortunately rather quite self-contained with our two-dimensional number system. You could easily wonder, is there a third-dimensional number system? Yes and no. There actually is not a three-dimension only system possible to construct that has any use to us. You actually have to go to 4 dimensions in order to create a usable, viable, useful three-dimensional system. That 4-dimensional system is called the quaternions. And I wrote about that in my book. Quaternions sort of had the physicists excited in the mid-1800s, and then they found better ways to handle this. But it turned out physicists discovered that two-dimensional numbers were great for handling calculations involving forces in 2 dimensions. And so they wanted a 3-dimensional system in which to calculate forces in 3-dimensional space. And later they came up with vectors. Math people created vectors, and that was much easier to work with than these quaternion system. The quaternions, incidentally, is a kind of a strange number system, and more rules of arithmetic break down in it. And so, in fact, you no longer have commutativity. If you multiply a times b in this 3-dimensional or 4-dimensional number system, a times b turns out to be equal to negative of b times a. So things get kind of strange there. We do lose a few things and gain a few things with complex numbers. One thing we gain is that there is a geometry to them, and one thing we lose is that how do you compare complex numbers? And in other words, how would you determine if one complex number was larger than another one? And there really is no less than or greater than that's sensibly useful in a complex number system. So we lose that sort of idea of size. Now, there is sort of a size. There, in fact, the absolute value of a complex number, I'll do this one, happens to represent the distance from the point to the origin, which is, the origin is simply the number 0. And so that distance, we call this the absolute value. I think it's also called a modulus, but I'll call it absolute value. And you could use the Pythagorean theorem, square root of 7 squared plus 5 squared. We're going to talk a lot about the Pythagorean theorem later on. But if you remember that this would be, let's see, 49 plus 25 is what, 74? Square root of 74. Alright, so the absolute value of this number is square root of 74. That may not have a whole lot of meaning for you right now, but it does have some meaning in some context in math and in physics. We can also, as part of this geometry, discuss its angle, and usually the angle we think about is the angle with the positive real number axis. And so this angle, which I'll call it letter theta for the Greek alphabet, we can calculate that number. I don't have my calculator at hand, but it's, as you can see, it's probably around somewhere between 30 and 40 degrees. So these complex numbers, which again are combinations of real and imaginary numbers, have a geometry to them. They're two-dimensional in character, and that's about as far as we go with it here. We are going to, you will need to learn how to add, subtract, multiply, and divide complex numbers, and we'll take that on shortly because it's part of learning the algebra. If you take our trigonometry course, then we'll delve into this geometry and trigonometry aspect of it, and I think it gets rather interesting. It's really not that hard either once you get into trigonometry to study this, and so it's another subject in that course there. I'll just leave it with this: adding and subtracting complex numbers has its geometry to it on the complex plane, and even multiplying and dividing has its own geometry to it. So there are geometrical things going on with the ordinary arithmetic operations in complex numbers, and so that's another thing you would explore in a trigonometry course. Okay, now we're going to go on to just learn how to do the ordinary arithmetic computations with complex numbers.